Alright, welcome. Today we're going to be taking some notes on refraction and Snell's law. So this is going to be in your notes packet. It's on page 12. We'll go through page 13 and we'll go through page 14 as well. So, to start off, definition of refraction. Well, what is refraction? Refraction is the bending of light. So we'll add this in. It is the bending of light when light travels from one medium into another. A good example of this is if you've ever looked at, say, water, and you've looked maybe beneath the surface of the water. Stuff beneath the surface of the water doesn't just look normal, it looks kind of a bit different, a bit distorted from what you might expect. This is especially clear if you have, say, a clear glass of water. If you just imagine looking through a clear glass of water, if you have one on you, maybe a water bottle, hold that water bottle up, look at something through that water bottle, and you'll see that the light coming in should be in some way distorted from how that object would actually look. So a good example, looking at a friend's face through a water bottle. The speed of light. Just like how sound waves travel with a set speed at room temperature, the speed of light, this is actually just a constant in the world of physics. There is a special variable that we use to distinguish the speed of light, and that variable is c. So how fast is the speed of light? How fast is c? It is 3 times 10 to the 8th meters per second. That is really, really, really fast. To be precise, 3 times 10 to the 8th is 300 million meters per second. If you compare that to the speed of sound, at least in room temperature air, is 343 meters per second. So the speed of light is about a million times faster than the speed of sound. It is the fastest thing ever. Nothing can ever go faster than the speed of light. Everything we're dealing with in optics is light in one form or another, right? There are parts of the light spectrum that are not visible. There's X-rays, there's gamma rays, there's infrared radiation, but it's all just light, so it all travels at this same speed. I do want to mention 3 times 10 to the 8th, this is the speed of light in a vacuum. Add a little caveat. When light travels through other mediums, it is actually going to slow down. We'll talk more about that in just a little bit, but in a vacuum it travels at 300 million meters per second. So what causes refraction? Well, refraction is caused by light changing speed going from medium to medium. So let's draw a little example. What happens in our refraction? If we go on to normal line and measuring angles, we're going to draw out, it's right here, and we're going to say, okay, we have an incident light ray. We'll do our incident light ray in blue. It's coming and going to hit this surface. And let's say we have air, excuse me, and then it is going to transfer into water. So down here, this is water. Up above, we have air. Well, we would draw in our normal line. Normal line is always perpendicular to the surface. So we'll draw this perpendicular to the surface, and we want to make our normal line dashed, of course. So let's go ahead, change this style, change it into a dashed line. Okay, so this is our normal line, just perpendicular to the surface that the light is making contact with. we would measure that incident ray starting at the normal line and going to our incident ray. This is the angle of incidence. And here we'll label it with a 1. Let's extend our normal line down into the new medium. We'll make this one dashed as well. And now, as you're going from one material into another, there's something you have to care about, and that is called your index of refraction. The index of refraction is going to tell you how much and what direction something should bend. But for context right now, just as an example, when light goes from air to water, it is going to bend closer to that normal line. So it will bend, and you'll end up with something like this. You could go through, you could measure then this angle from normal line to that refracted ray. Remember, it's not reflected. It passes through and changes direction. It was going in a straight line path. It enters a new medium, and it changes direction. It doesn't have to be a huge change in direction, but slightly changes direction. And this is now our second angle, the angle of refraction. Alright, let's talk about index of refraction, sometimes referred to as optical density, but usually we'll just be talking about index of refraction. Index of refraction is essentially a number. It is n. And index of refraction is on this sliding scale, really all the way from air down to more optically dense materials like, say, glass. There are a few more on this sliding scale, but we'll start with just these two. Air has an index of refraction of 1. Glass has an index of refraction 1.5. Water is in the middle. It has an index of refraction 1.33. Essentially, what this is measuring is it's measuring how much light slows down in the medium. So we can add in glass, slowest in glass. At least among these materials, air, water, and glass, light is the slowest in glass. It has the highest optical density. It has the highest index of refraction. This is what determines what direction light is going to bend. If you go from a less optically dense medium into a more optically dense medium, there's a few different ways you can memorize this. There's a few different mnemonics that we can use. We'll start off with two little mnemonics right here. Let's give context. Air had an index of refraction of 1. Water had an index of refraction 1.33. So, you are going from a less optically dense medium to a more optically dense medium. It bends towards the normal line. One mnemonic you could use is a little rhyme. This was what I was taught in high school, is less to more. Talking about the index of refraction, going less to more, your ray, your light ray, is going to bend toward, kind of like toward the normal line. But we, of course, say toward to make it rhyme with more. Remember, we're doing a little bending of English here. Less to more bends toward the normal line. Then, if you're doing the opposite, imagine there's a situation where you are going from water and then from water into air. Well, you might imagine that is going to, let's actually just go ahead and extend this line. We can do another little example. Let's get our normal line sketched out right here. Of course, make that normal line dashed so we don't think it's a light ray. Then we'll draw in light coming in, incident onto the surface. We'd say, okay, this is our angle 1. It's coming from the water, leaving the water, entering the air. It is going from a more optically dense medium, a higher index of refraction, to less. So it is going to digress. It is going to move away from, bend away from that normal line, like this. And again, to measure that angle, it's always start from your normal line and measure to the ray. So here, this would be theta 2. Okay, so less to more bends toward the normal line. Let's go ahead and lasso this, bring it on over. Then what's the rhyme earlier? Well, I said it. More to less does digress. So if you're a poet and you didn't know it, here's some rhymes to help you remember. Look at your index of refraction. If it is less to more, you're going to bend toward the normal line. That's going from, say, air into water. If you're going more to less, it does digress. Digress meaning moving away from the normal line, like so. Going from water into air, more to less. Now, if this is a bit too strange of a mnemonic to use, there is an acronym that you could use instead. And that I will give you down below. Do a little squiggly line. The first acronym is FAST. If you're going from a material that light travels really fast in to a material where light travels really slow in, you bend towards the normal line. So fast to slow. The bigger the index of refraction, the slower light is going to travel. So light travels faster in air than in water. So we're going from fast to slow, and you bend toward the normal line. Again, this is less to more, bends toward normal. What is the acronym for going more to less, right, if you don't want to use the rhyme? Well, this is going to be SOFA. You go from a slow medium to a faster medium, that is going to bend away. These mnemonics, they both work. They just take some getting used to. You could use both. You could pick one. I personally always use less to more bends toward, more to less does digress. That's just how I learned it back in the day. That's easy for me. But FAST and SOFA absolutely work as a device to help you remember. All right, let's make sure we're still recording. Oh, it's more than I need. There we go. Okay. Snell's law. Now this is the actual math of refraction. How do we determine how much something is going to bend towards or away from normal? Well, Snell's law is very simple. It is just going to be n1 sine theta 1 equals n2 sine theta 2. And now keep in mind, n is the index of refraction. And from our diagrams before, you can see, oh, theta 1. That's the angle the light is coming into contact with that new medium at. That's the incident angle. Then, angle 2, theta 2, is going to be the angle the light enters the new medium and refracts to. So that's the angle of refraction. And then you just simply plug them in. So, for an example, let's take this information and say, oh, what would we actually be able to do with it in context of a problem? Well, here, let's apply Snell's law. Back up on page 12. N1 sine theta 1 equals N2 sine theta 2. Okay, let's make up an angle that this light is coming in at. Let's say, and I know I didn't draw it exactly like this, but let's say it's coming in at an angle of, say, 30 degrees. Okay, well, the index of refraction of air is 1. So we're going to start off, everything for air will be on one side. We'll plug in that index of refraction of 1. There's no units, no need to worry about plugging it in. And we're just going to multiply 1 by the sine of 30 degrees. Okay, then set this equal to, well, our right-hand side, N2 sine theta 2, that's our information for the water. So our index of refraction in the water, 1.33 sine of our angle, theta 2. This is our unknown, that's what we're looking to solve for. And now we can just go ahead, grab our calculator, let's pop out, bring ourselves over to a calculator, and actually calculate. Something I always recommend, you want to make sure that you are in degree mode. So double check your calculator, make sure you're in degree mode before you do your calculations. Let's bring notability back, and we can just plug in. So right up here, we can say, all right, sine of 30 degrees gives us 1/2 as expected. Multiplied by 1, of course, that's not going to change anything. We get 1/2. Okay, so our left-hand side here is really just 1/2 equals 1.33 sine theta 2 divide by 1.33. Okay, we get 0.376. We can round. So let's continue on. We'll write this in green just to keep track of it. We're taking 1/2, and we are moving over the 1.33 by dividing. So now on our left-hand side, we have 0.376. We'll do some rounding, equals sine of theta 2. Now, how do we solve for this? Well, we have to do some inverse trick. So that means take the inverse of sine, plug in that decimal. Inverse sine of 0.376. That is going to give us the angle. So we go through, we say, okay, take the inverse sine. Oh, hit the wrong button. Inverse sine, there we go. 0.376. What answer pops out? That is our angle theta, 22.09. We'll round. And that is theta 2 we should list. Now let's check, make sure that makes sense. Okay. So if this light coming in right here was coming in at a 30-degree angle, it would refract the angle of refraction right here. That would be 22.09 degrees. That is smaller than 30 degrees, and that is what we talked about with our acronyms. You're going from a less optically dense medium to a more optically dense medium, less index of refraction to more index of refraction. You're bending toward the normal line. You're going from a fast medium, the air, to a slow medium, the water. That's going to bend towards your angle of refraction is smaller than that angle of incidence. And this is how you use Snell's law for anything. It won't always ask you to solve for an angle. Sometimes you'll be given the angle of incidence, the angle of refraction, and you need to solve for one of the indexes or indices of refraction. Two last things to talk about: how to draw a refraction rate diagram and total internal reflection. Okay, so how to draw a refraction rate diagram. Well, let's go ahead. We have our air. We're going to start off with a normal line. Make sure to make it dashed. Okay. Then we're going to go from air to glass. Now remember, air has an index of refraction of 1. Glass has an index of refraction 1.5. So let's use our rules. Let's practice. We're going from less to more. So we're going to bend toward the normal line. Now, if we knew what angle we were coming in at, if we knew this angle of incidence, then we can actually calculate exactly what angle we were going to refract at. But we don't have that information, so we are just going to say, well, we know we're bending toward our normal line. So it should look something like this. Or again, this angle of refraction right here, it is smaller, it's closer to the normal line, we're bending toward normal. Then we go through the glass, travel in a straight line. As long as you're not changing mediums, you're going in a straight line. And now we will do another normal line right here, because when the light passes through the glass and it eventually reaches the end of that glass, it will pass back into the air. So we will go ahead and we'll say, okay, well now we have some light coming in right here at this angle. If you did a little geometric proof, you can actually see that this angle and this angle are alternate interior angles. So they must be the same. And we are going from glass, index of refraction 1.5, to air again, index of refraction 1. We are going from more to less. So we're going to digress, we're going to move away from our normal line. And we could measure angle right here. That's our angle of refraction, going from glass to the air. Something neat about this is, since you started in air and you end in air, these angles, theta 1, theta 3, should actually be the same. Because if you're going in at this angle, you should actually be leaving, as long as you're ending up in the same substance at the same angle. It's just the light got bent while it was traveling through the glass, changing where you see something if you're looking through, say, water or glass. Okay, total internal reflection. Let's make sure we're still recording. Lovely. Okay, for total internal reflection, what is going on? Well, alright, for total internal reflection, well, let's look at this picture off to the right. What we really have is light coming in, going from one material to another. And you can tell if, well, light is coming from up here, and look at this example, we are bending toward our normal line. That means we are going from less to more, because less to more bends toward normal. But if you compare how much bending is happening, you'll see if the light is coming in at a really, really steep angle, it is going to bend a good chunk. Whereas if you're coming in at a smaller angle, it is going to get closer and closer and closer to normal. Whereas if eventually you get to where light is coming in totally perpendicular to the surface, it's actually not going to refract at all. Same thing, leaving. Here we are going from more to less. So we are going to digress, we're going to move away from normal. Drawing your normal line, well here, this is the normal line. If you come straight on, in line with the normal line, parallel to it, you're not going to refract at all. Whereas right here, you do start to refract. And as your angle of incidence increases, as you're coming in at a bigger and bigger angle, your angle of refraction also increases. And now this keeps happening, and you might ask yourself, well, what happens when eventually your angle of refraction hits 90 degrees right here? Well, this is called a specific angle. It's actually going to be the critical angle. When light comes in and is incident on a surface, it is going to hit a surface, going from one medium to another, and it is coming in at an angle greater than the critical angle, it is no longer going to refract. It will now do something called total internal reflection, and that is right here. So, if you have anything greater than or equal to this angle, that light, it is actually going to bend so much that it just ends up staying within the same material. If light comes in at this angle, this is an angle greater than the critical angle, the light experiences total internal reflection, and it actually does not enter the new medium. It won't go from the more optically dense material to the less optically dense material. It will just reflect off the boundary and go back into the more optically dense material. Now, let's add this in. If a light ray in a material strikes another material at the critical angle, what is the angle of reflection? Well, again, we're measuring from the normal. That happens in our picture right here. So this is the critical angle. That means this is just when total internal reflection has started. This angle right here is a right angle. That angle of refraction is 90 degrees. If the angle of incidence is less than the critical angle, what happens to a light ray that strikes a surface between two materials? Well, it will refract into the second material, and it depends if you're going from a more optically dense to a less optically dense, or less to more. Again, both cases are possible. In one case, you bend away from the normal line. In one case, you bend towards it. But as long as it's less than the critical angle, regardless of whether you're going to bend toward normal or away from it, when a light ray strikes a surface between two materials at an angle of incidence less than the critical angle, that light is going to refract into new material. If the angle of incidence is greater than the critical angle, what happens to a light ray that strikes a surface between two materials? Well, it is going to totally internal reflect. So all the light reflects and remains in the original material. And this must follow the law of reflection. So in that case, if you get total internal reflection, that means that the angle of incidence must equal your angle of reflection. No more refraction. Okay. Lastly, there's some critical angle values for water and air, glass and air, and diamond and air. Well, going from water to air, this is going from more to less. You're bending away. Critical angle value here is 48.6 degrees. So if light is coming in, going from water to air, at an angle greater than 48.6 degrees, it will experience total internal reflection. It will reflect internally rather than enter the air and refract. Going from glass to air, 41.1 degrees. Again, anything greater than that, and you get total internal reflection. Anything less than that, and you get refraction, entering into the new material. And if you are exactly at that angle, that is when you get this 90-degree refraction. And if you're going from something like a diamond into air, that would be 24 degrees. So if we're asked our last question, where is total internal reflection more likely, between water and air or between glass and air? Why? Well, it is more likely between glass and air. As the critical angle is smaller. With this, take these notes, work on reflection practice, page 15, 16, and 17. Next class, we'll be taking our curved mirror check. We'll go through some notes together, do a little recap, and then move on from there. Again, your homework is to work on pages 15, 16, and 17. This is really the last little bit of content for this unit, so feel free to get a jump start on our review packet that you can find in Schoology. There will be an answer key for pages 15, 16, and 17 to follow, as well as an answer key for the review packet as well.